Good day, distinguished colleagues. In this year revision course, I'll be taking the lecture on medical statistics. I will be focusing on some basics and application of statistics. My name is Adebola Orimadegun. At the end of this lecture, I would expect that everyone should be able to mention and define some biostatistical terminologies as well as their uses. I would expect that you will be able to relate effectively with biostatisticians on problems requiring biostatistical tools. Lastly, I wish that you are able to read and understand and judge the appropriateness of the use of statistical concepts and tools used in health literature. Let's begin the lecture by defining data and variables. Data are distinct pieces of information, usually formatted in a special way. Strictly speaking, data is the plural of datum, a single piece of information. In practice, however, people use data as both the singular and the plural form of the word. A variable, on the other hand, is something that varies between individuals or items. Information is collected from studies and study group by recording everyone's value for the relevant variable. So, we define this as variable. Define anything that can be quantified or qualified and varies as variable. A simple example of variable is height, that is measured in centimeter, which vary from person to person. Other examples may include items that can be counted or measured. In a study to assess the effect of giving recombinant human erythropoietin, for instance, to premature infants, the investigator may measure hemoglobin level and the number of transfusions required, and this constitutes variable on their own. But the quantity in itself constitutes data, and those are the piece of information I referred to. Maybe it may be relevant variable to record in this instance, it may be relevant to record in the treatment to receive, whether you may, and the investigator may choose to have those in the treatment group or in the placebo group. So those are study groups, but variables are those quantity or qualities that are described. And the way they are described is in the form of data. So it is important to consider the variable types when deciding how to display or analyze a study results. So everyone needs to understand the kind of data and variable required for their study. In general, there are two types of variables. All variables can be classified into two broad categories: categorical and numerical variables. Categorical variables are those that define the classes or categories in which an individual or study participant falls. Numerical variable, on the other hand, are variables to which a number is assigned as a quantitative value. So it depends on the number of categories, whether there is an ordering or to them or others. What am I trying to say? That categorical variables can take three different forms also. It could be two possible outcomes, which we refer to as binary, or it could just be in the form of naming, which we refer to as nominal or ordinal, when it takes a particular order in its arrangement. For instance, individuals are classified by their blood group as either A, B, AB, or O. This type of variable is categorical and it is just merely nominal. In other words, you cannot quantify, there is no relativity between A, B, or AB or O, but just to classify people. Meanwhile, for numerical variable, you can have values in between values. For instance, You can talk about total rainfall measured in inch, or the heart rate measured per minute, or the number of sugar consumed in a day. All these, you can assign number to them, unlike categorical variable. Some people also describe categorical variable as qualitative variable. Types of categorical variables. We have ordinal variable, nominal variable, or binary variable under the categorical variable. If there are two or more categories and the categories have an obvious order, either increasing or decreasing order, then you refer to this as ordinal variable. For instance, social class could be 1, 2, 3, 4, or 5, and you consider this in increasing order. Or you can have an order that depicts a grading in terms of pain score or pain scale. It could be none, mild, moderate, or severe. Or it could be on a scale of 1 to 10, with 1 being the lowest and 10 being the highest. So this, when you have this type of uh, variable, it is referred to as ordinal variable. But for nominal variable, which is another type of categorical variable, this simply imply just names. For instance, ethnicity. There is no difference between one ethnic group or the other. So you can't particularly talk about any other. You are either Yoruba, Igbo, or Hausa, or any other tribe whatsoever. Or you are either married, not married, divorced, or separated, or widowed. So a variable of this nature is regarded as nominal variable. But for binary variable, if there are only two categories, then the variable is known as binary or dichotomous. So binary variable are common. You talk about dead or alive. You talk about low or normal birth weight. You talk about male or female, yes or no responses. These only assume two possibilities. Numerical variables are either discrete or continuous, although the distinction is only important if the variable is discrete with relatively few values. Discrete variable reflects a number obtained just by counting, and this variable cannot assume a decimal place. If the numeric variable can take the form of only a distinct number, usually complete integer, either 0, 1, 2, or 3, and so on, then it is known as discrete. For example, age in years. When age is in year, it cannot be 2.4 years. Or parity. You can either have one child, two children, three children, not 1.2 children. Number of visits to clinic. Number of visits to clinic can only assume a whole number, but not a decimal. Those are examples of discrete variable. For continuous variable, this kind of variable reflects a measurement on a continuous scale. The number of decimal places depends on the precision of the measuring device. Therefore, we talk about scale of measurement. So continuous variable can either be on ratio scale or interval scale. For instance, example of ratio scale will include measurement like height, weight, and blood pressure. In this instance, we have order and distance, and the difference can be compared because it has a true zero value. So ratio can be compared in this instance. But for the interval scale, the order and instance and distances are also implied, but the difference can only be cannot be compared because there is no true zero. For example, temperature that is measured in Celsius, you can hardly have a human being that has a temperature of 0. But in that instance, the person surely must have been dead. So, however, there are instances where we change the form of continuous variable. You can convert a continuous variable to a categorical variable by grouping them or having a cutoff. Or you can convert a continuous variable to a discrete variable. For instance, blood pressure can be reclassified as either high or low. And that in that situation, you have hypertensive or normotensive, and that becomes a binary variable. Birth weight also may be divided into less than 2.5 kilogram and greater than 2.5 kilogram. And this gives you low batch weight and normal batch weight. So you can also classify number of clinic visits, and it will become 0, 1 to 3 visits, 1 to 4 visits, and so on. Then it may be turned to ordinal form. So you can move from being you can move a variable from being continuous to categorical variable or ordinal variable, depending on your interests that you want to measure. Let's talk about the difference between independent and dependent variable. An, an independent variable is such that the investigation control or manipulate. The researcher is the one that is manipulating or changing the independent variable in an experiment. You can also think about independent and dependent variable from the point of angle of cause and effect. An independent variable is the variable you think is the cause, while the dependent variable is the effect that you observe. So in a nutshell, you measure the dependent variable, which is a function of independent variable. And mathematically on a graph, we plot independent variable on x-axis, while the dependent variable is often plotted on the y-axis. In medical statistics, we are either referring to a population or we are talking about sample taken from population. So in research, generally, we have target population, which is where the sample are taken. And the reason why we need sample is because it's almost impracticable most of the time to study the entire population when we want to do research. Therefore, we take representative sample, and from here, we then determine statistics. So when you determine statistics, the estimate you are getting, the intention is to be able to generalize it to represent the population. So a sample is a subset of a population, while the population is the entire element of the research or the investigator is trying to imply. So we rely on sample to make inference and that is where we calculate statistics from. So the estimate obtained from samples are referred to as statistics, while the estimate of a population are referred to as parameters. So very commonly, for instance, we refer to mean of a population as parameter, whereas the mean of a sample is known as the sample mean. And we often would like to infer from the sample mean what is the true value in the population. So this is what we try to do at every point in time when we talk about statistics. If we estimate a mean, for instance, we usually describe the interval in which the true value will be within population, either by giving what is known as confidence interval or talking about the standard deviation, a measure of variability. And I will talk about this more in subsequent slides. A statistic is a quantity calculated from a sample, as I said earlier on, and this describes a particular feature. Statistics are always estimates. Parameters are descriptive measure of the entire population. However, their values are usually unknown because it is infeasible to measure the entire population. Because of this, we usually would like to take a random sample from population in order to obtain parameter estimates. One goal of statistical analysis is to obtain estimate of the population parameter along with the amount of error associated with this estimate. These estimates are also known as sample statistics. A fitted distribution line is a curve based on the parameter estimate instead of a true parameter value. There are several types of parameter estimates. One, you can have point estimates, that is one single measure, most likely value of a parameter. For example, the point estimate of population mean, which is parameter, is the sample mean of the estimate. So usually we make an inference from the sample mean. Or we can have a confidence interval, which are a range of values likely to contain the population parameter, as I said earlier. There are two types of statistics. It could be descriptive or inferential. Descriptive statistics are used to provide description of the population, either through a numerical calculation or graphs or tables. So this form of statistics make inference from frequency, mean, median, mode, minimum, maximum, range, standard deviation, skewness, or kurtosis. Whereas the inferential statistics, you make deduction from it or prediction about cause and effect or about relationship between variables about a population based on the sample that was collected from the population in question. So classically, we use test. We talk about testing of hypothesis when we are referring to inferential statistics. So we can talk about t-test, chi-square, f-ratio, ANOVA, and so on. So I will talk more about this later on. However, let's make distinction between descriptive and inferential statistics. Descriptive statistics is also a form of discipline which is concerned about describing the population. Descriptive statistics collect, organize, and analyze data presented, but on the contrary, inferential statistics do comparison. You test hypothesis in inferential statistics. So there is a diagrammatic or tabular representation of the final result when you talk about descriptive statistics. But in the case of inferential statistics, you talk about hypothesis testing, you talk about significant difference, you talk about correlation, you talk about regression, you talk about prediction, you talk about making deduction based on a predetermined or pre-formulated theories. As I said in the previous slide, for descriptive statistics, we summarize, organize, and simplify data. So first, the raw data is made into a manageable form and then presented in a logical form, and then a pattern may be described or a shape may be formed using frequency table, graphical technique, and measure of central tendency, as well as the spread or measure of variability. All these constitute descriptive statistics. Still talking about descriptive statistics. So measure of standard tendency simply refer to single value that attempt to describe a set of data around a central position within the set of data. There are three main measures of central tendencies. These are mean, median, and mode. Mean refer to the average of the numbers or the measurement, whereas the median is the middle number when those measurements are arranged in a particular order, either descending or descending. And mode is the most frequent of the values recorded or measurement recorded. For measure of dispersion, we simply imply spread around a particular value. So these are measures of the extent to which the distribution is stretched or squeezed. So we talk about how spread out a set of data is when we talk about dispersion. An example of statistics for measure of dispersion are variance, standard deviation, standard error, range or interquartile range, or absolute deviation. In the next 2 or 3 slides, I would just like to illustrate descriptive statistics using this data that you're seeing on this slide. We have a researcher who is investigating a short-term memory capacity of how many symbols remembered by participants, 20 participants in all, and these were recorded as follows: 4, 6, and so on, as you have seen it. So we can describe this data by using frequency distribution table, and this can be presented also in form of a table or a graph. So always present the set of category that made up ordinary category in this way, and the frequency of each score category. So 3 important characteristics can be used to describe this data. We can talk about the shape, we can talk about central tendency, and we can talk about variability. Now, for frequency distribution table, so this table can be presented in this format. You have a table which shows the list of the possible items and how frequent they occur, and then the multiple of the item and the frequency. So the highest score is at the top in this case, and all the observed scores are listed. Please, then we can get more information about the distribution by calculating first the mean. You can talk about the standard deviation, and we can talk about centrality of the data by referring to mean, median, and the mode. The mean in this case is the sum of x divided by the number of items, which is capital N, as shown in the formula. Now, We can also present this same data in this format. After presenting the table of frequency, you can calculate percentage of each item contributed in this way, and the column P is showing the proportion, which is in decimal anyway, and the other one, the next one to it, to the right, is showing the percentage contributed by each of the items. So the frequency table can display more information in this way by showing percentages and proportions. And from this table, you can answer questions such as how many participants remember 7 and above. Okay, and that will be can be calculated from these proportions. So what does this tell us about the distribution of the score? You can always answer such question from here. Now, we can also present the same information in a group frequency manner. Of course, this is referring to a totally different data because we don't have values that is as either. But this is called group frequency distribution table, whereas you can talk about class, the class interval, talk about lower and upper class, upper values of the class. So the class interval represents continuous variable x, and then the boundaries are in this case, the first one is 95 and the upper boundary is 99. We can also present it in form of percentile and percentile rank. Percentile chart, this in particular will help to answer the question I did ask earlier on. For instance, how many people score 7 and above? You can see it from here. Okay, that from uh, from here that you have a cumulative frequency. This is 10% at 3, and then by the time four people, then the cumulative frequency is increasing in that order upward, and 4 people, for those who score 4 and below are 25% of the entire group, and those who score 7 and below are 70%. Those who score 10 and below, 95%. And so that's what cumulative frequency can tell you. Now, other measures of central tendency include the mode. As I said earlier, mode is the most frequent value in the distribution, but it does not take into account all the other values, and that is one of the merits of mode. So mode will not be the best of measure of distribution if, for instance, you have many values that are extremes. So mode is unaffected by the extreme, so not useful when there are several values that occur equally. That is, if the most frequent value happens, for instance, in the example we saw, if people who remember 5 items and 4 items of the same number, it is difficult to tell which one represents the mode in that case. So sometimes a set of data may have more than one mode. Now, for the median, which is the central value when the data are arranged in a particular order, whether descending or descending, the value that falls exactly in the midpoint is actually the median. So, but for median does not consider exact scores. We're just like the mode, so it's unaffected by extreme score, but in a small set, it can be unrepresentative. So the middle value may not represent the data well when you have a small number of data sets, but when it is large, it is. And then one other thing that to consider is the distribution. If the distribution of the data is skewed, then the median may be a better choice than the mean. But when the distribution is normally distributed, then we use the mean rather than the median. I'll talk more about this when I've explained distribution of data in subsequent slides. So for the mean, of course, we all know that it is the average of all the values present in the data. We can represent continuous variable using graphs, and one of such graphs is the histogram. As you can see from these diagrams, The bar width of an histogram represents the limit of the class interval, while the histogram blocks actually represent the individual score. And on this slide, you have three different ways of presenting such data. Yet another way of presenting a continuous variable is the use of frequency distribution polygon. This shows the shape information with line and traces shape of the distribution. And you will observe from the diagram above that the histogram is actually turned to the um, frequency polygon by using the midpoint of the each bar and joining the lines in this way. Both histogram and polygon represent continuous data accurately. For more numerical data, frequency distribution can be represented by bar graph. I mean non-numerical data can be represented by bar graph, which are separate bars, as you can see in the diagram below. Still talking about distribution of continuous variable. When a frequency polygon is done or data are plotted as you can see in the chart before you, we can assume it can assume several shapes, but the commonly referred to kind of shape in statistics is the normal distribution shape, which is represented in the diagram you are seeing. The normal distribution is the probability function that describes how the values of a variable are distributed. It is a symmetric distribution where most of the observations cluster around a central peak and the probabilities for values further away from the mean taper off equally in both directions, to the left and to the right of the mean. Extreme values in both are located in the tails, either to the right or to the left in a similarly unlikely manner. The distribution of data, particularly continuous variable, is key when we talk about statistical tests. And this is the reason why I'm going to spend a few minutes talking more about it, because the assumption that underlies the use of statistical tests is the way the data is distributed. So most statistical tests assume normal distribution, and a normal distribution in statistics depicts a bell-shaped distribution, which uh, which can be defined as an equation symmetrical around the midpoint, as I've said earlier, where the greatest frequency of the points could represent the mean as well as the mode and the media, all at the same central point. Normal distribution is an assumption that is made in parametric tests. It is important to note that it is not at all times that we have data distribution assuming the normal shape. Sometimes it could be asymmetric, and which we refer to as skewed distribution. When the distribution is skewed to the right side, then we talk about positive distribution or positively skewed distribution. But when it is skewed to the left, we say it is negatively skewed distribution, as you can see in the diagram before you. Whenever you look at the shape of a distribution and the tail is pointing towards the right side, then it is positively skewed. When the tail is pointing towards the left, it is negatively skewed. Sometimes we have data that have two modes, bimodal data, and that is the kind of shape you see in the right upper hand corner of the slide you are looking at. There are certain characteristics that define a normal distribution or a normally distributed data. What is then a standard normal distribution? The standard normal distribution is also known as Z distribution. It's a special case of normal distribution where the variance is always the same. The mean plus or minus one standard deviation contains approximately 68% of the total variation of the data, while the mean plus or minus two standard deviation contains about 95% of the total variation, and the mean plus or minus three standard deviation contains the 99.7 rather of the total distribution. What is the implication of this to us as clinicians? Very often we talk about reference value. The intention of normally plotting distribution of data is such that if we know a particular value of a parameter in the population and the distribution tends to be normal, we can we assume that a certain standard deviation represent individuals who are normal and those who are at the extreme are abnormal. So very often we use the 95% of the total variation. This graph is an attempt to show you what a normally distributed could sometimes look like. Why? It is important to look at the shape of your data anytime you are doing statistical analysis, because as I said earlier on, most parametric tests actually assume a normal distribution. So if the shape of the histogram is not looking like this, it is better to assume that it's not normally distributed and then choose the appropriate test, which I will talk about later on in the lecture. Still talking about the skewness of data distribution. From this diagram, you can see that when the data is skewed, the mean, the median, and the mode, they are in different positions. That is, they have different values. But in normally distributed data, the mean, the median, and the mode, they have the same value. So look at this diagram carefully. Look at the mode is at the peak of the graph where the mean is shifted to the left, to the right rather, and the median further to the right as well. But when it is negatively skewed, then this graph is turned to the opposite direction. In other words, we then have a mode that is greater than the median and the mean. So, but the standard deviation is very often as shown in the diagram. I have decided to put these two side by side to further illustrate my point. Look at positively skewed data and the negatively skewed data, and look at the position of the mode, the median, and the mean. You could see that they vary, but in the normally distributed data, the mean, the median, and the mode are on the same point. You will recall at the beginning of this lecture, I talked about the fact that we use samples to represent the population, and what we calculate from sample is known as statistic, and what the true value should be in the population are parameters. So when we take sample from the population and we estimate a particular value, for instance the mean, we want to know how far away from the truth it is. Therefore, we talk about variability. We want to describe an exact quantitative measure, how spread out or clutter around the actual score is our estimate is. So variability is usually defined in terms of distance, that is how far apart scores are from each other, or how far apart scores are from the mean, or how representative is a score of the data out of the set of a whole. So there are three main ways to summarize the variability of a set of data. We either give the range of all values, or we calculate a single numerical value of the dispersion around the mean, which is known as standard deviation, or we quote the percentile within the data. In describing variability, the range simply represents the difference between the highest and the lowest of all the values. The range only takes into account the two extreme score and it ignores any other value in between. So to counter this problem or concern, the distribution can be divided into quartile, and we talk about quartile, then we have the lower quartile and upper quartile, and then we talk about interquartile range as an alternative measure for a range. So it is better, if you have to present a variability in the form of a range, it's better to talk about interquartile range, so you can take into account the values in between the minimum and the maximum. A more sophisticated measure of variability is the one that shows how scores clutter around the mean, that is the standard deviation. Deviation is the distance of a score from the mean, and a measure that represents the variability of all score, rather instead of using the range or interquartile range. But there are instances in which you cannot calculate standard deviation and you just have to state the range. For instance, when the data is not normally distributed, it is better to represent the center of tendency using a median. Then in that instance, the appropriate measure of variability will be the range or the interquartile range. You will recall the formula for calculating standard deviation shown in the previous slide. Therefore, for us to be able to remove the plus or minus sign, we often talk about variance, and that is simply mean we square the deviations, the sum of deviation before we find the average. Therefore, standard deviation is the square root of variance. Mathematically, the population variance is designated as sigma squared, as shown in the notation on the slide. So the sample variance is designated as S squared. In other words, the square of the deviations. So in order to describe this more appropriately, mathematically, we talk about the degree of freedom, which is the number of independent free to vary score in a sample. The sample mean must be known before the variance can be calculated. Therefore, the final score is dependent on earlier score. That is, the degree of freedom is the total number of data minus 1. Describing variability still, the standard deviation variance is a measure based on the squared distance. In order to get around this, we can take the square root of the variance, which gives us the standard deviation. The population and sample standard deviation are as denoted in the formula. Please note that the standard deviation is the most common measure of variability, but the others also can be used. A good measure of variability must be stable, reliable, must not be greatly affected by little details in the data. That is, a stream of scores should not affect it. Multiple sampling from the same population should not affect it, and open-ended distribution should not affect such parameter. So both variance and standard deviation are related to other statistical techniques. What does this mean? It means that if you have to repeat the same sample within the same population as many times as possible, the standard deviation should be the same, even if you are getting slightly different means, because it describes to what extent the true value vary and within which limits should we believe your estimate as the true representative of the population. Before we conclude our talk about descriptive statistics, particularly measure of central tendency, let's highlight some of the properties of the mean, median, and the mode. The mean is sensitive to outliers. The others are not. For example, a single data point which is a very high value may increase the mean by an appreciable amount. The mode, on the other hand, may be affected by small changes in the data. The others are not. If two categories are almost equally common, slightly change in the data may affect which is the mode. The mode and median may be found graphically. For example, the median can be found from a cumulative frequency, histogram, or polygon. All the three measures of location are equal for a symmetric distribution. That is, for a normally distributed data, mean, median, mode are equal. But in a skewed data, they differ remarkably. One important question that we should always ask ourselves is, which measure of location should I use? Generally, for skewed distribution, the median is a better summary measure of location than the mean. For statistical analysis and inference, the mean is more often preferred. However, if the data is considerably skewed, that is, it's not normally distributed, then it may be more appropriate to use transformations. That is, you transform either through by find the log of the values, then find the average, and then convert it back to arithmetic mean. Or you just simply state the median and the interquartile range. You will recall that I told you earlier on that all statistics can be divided into two broad categories or described as either descriptive or inferential. So now we have talked about descriptive statistics. It is time to talk about inferential statistics. So in inferential statistics, we answer the question, can your experiment make a statement about the general population? In other words, can we make an inference or a deduction from your experiment using statistics? One fundamental requirement for anybody to carry out an inferential statistics is that a random sampling must have been done. In other words, every element in the population must have been selected based on a known probability. In a random sample, each item of element of the population has equal chance of being chosen at each draw. A biased sample is one in which the method used to create the sample result in samples that are symmetrically different from population. That is, if you do distribution of that data, it should be close to a normal distribution. Otherwise, then it does not represent a random sample. In inferential statistics, there is the need to have stated hypothesis earlier, and that is what we often test when we talk about inferential statistics. An hypothesis is a statement of guess, a statement that assumes no difference. Usually, we talk about that as a null hypothesis. So, the 5 main steps in testing hypothesis during inferential statistics is first, that you state your hypothesis as in the null form and then state the alternative. For instance, we may want to find out the difference between the average height of boys and girls in a particular school, and then we then say our hypothesis in the form of there is no difference in the mean height of boys compared with girls. So, and the alternative will be that there is difference. So, after stating this hypothesis clearly, we collect data in a way designed to test the hypothesis. In other words, we collect data on the required variables and then perform a pre-statistical test. I have highlighted this in red because that is the focus of this lecture in this section. So then decide whether the null hypothesis is supported or refuted. You present the finding in your results and then the discussion session. So in statistical tests, particularly in inferential statistics, everything centers around the null hypothesis. So by the time you now do the test, you conclude whether to reject or do not reject the null hypothesis. I will explain further in subsequent slides. What does a statistical test do? Statistical tests work by calculating a test statistic, a number that describes how much the relationship between variables in your test differ from the null hypothesis. So we find out the probability of either rejecting or not rejecting null hypothesis. This is what we call p-value. So the p-value estimates how likely it is that you will see the difference described by the test statistics if the null hypothesis of no relationship were true. If the value of the test statistic is more extreme than the statistic calculated from the null hypothesis, then we infer that there is a statistical significant relationship. But if the test statistic is less extreme than the one calculated from null hypothesis, we infer that there is no statistically significant relationship. When do we perform a statistical test? For a statistical test to be valid, your sample size needs to be large enough to approximate the true distribution of the population being studied. To determine whether statistical tests to use, you need to know whether your data meets certain assumptions. And one of such assumptions is that the data should be normally distributed. And we also need to know the type of variable that we are dealing with. Here are the statistical assumptions that we make when we carry out statistical tests. First, we assume independence of observations. That is, the variable that we are testing are not related. Second, we assume homogeneity of variance. That is, the variance within each group that we intend to compare is similar among all groups. If one group has much variation than the other, it will limit the test effectiveness. The third assumption is that we assume normality of data. The data follows a normal distribution. This assumption applies only to quantitative variable anyway. So if data do not meet these assumptions of normality or homogeneity or variance, a non-parametric test should then be used. This table before you summarizes the different type of statistical tests that are available, and for you to make a choice of which statistical test to use, you need to consider your study objectives and then decide whether you need parametric or non-parametric data, which is based on the whether your data is normally distributed or not normally distributed. I will not be able to explain this much in great detail, but I believe this table is simple enough for anybody to understand. Because of our time, let's move on. I have put this diagram again to further illustrate the choice of statistical tests, and I believe this simple algorithm will be a good guide for everyone who intend to carry out research and decide on choice of statistical tests to be used. In the next few slides, I've attempted to explain some of the tests and the conditions for which they are used. I've talked about regression tests in this slide, and simply put, regression tests are used to test cause and event, and there are three types: simple linear regression, multiple regression, and logistic regression. Then I talked about comparison tests, which include the test of mean. Either you are using t-test, ANOVA, or MANOVA. I believe the slides are self-explanatory, and particularly if you follow the algorithm I showed earlier, you should be able to apply some of these tests. In any case, many of you will be using software, but it is important to have the understanding or the basis for which you are making the choice of the test. Again, on this slide, I'm showing correlation test, which is an attempt again to find out the relationship between two variables, but in this case, you are not interested in the cause and effect relationship, but rather you just want to show whether these two variables have a similar variation, and so that you can progress to use the two variables in a regression test. Now, I would like to talk about the difference between parametric and non-parametric tests. So, the parametric tests you will have observed simply depict an assumption of normal distribution. So it is the assumption we make for a statistical test by default. But when all these parametric test assumptions are not met, then the alternative test is to choose the non-parametric test. So we have examples of parametric and non-parametric. For parametric tests, for instance, the equivalence of student t-test is Mann-Whitney U-test, and so on and so forth. Please refer to the table I showed you earlier to have a clearer picture. Very quickly, I would like to talk about how to write a statistical analysis plan, because I have noticed that many residents have challenge in doing this. So a good statistical analysis plan should state the dependent and independent variable, which I have defined earlier, should state the summary statistics of participant data, and state the assumption underlying statistical test they are going to use. So please remember to specify the statistics that will address each of your objective or each of your research question. Don't just state there that I'm going to use SPSS or mention the software, but rather state exactly what test you are doing and for what reason why you are doing it. Justify why you have chosen the appropriate test, statistical test, and state how you will account for other variables, covariates, confounders, and effect modifier. Please help yourself by checking out the meaning of each of these, and then provide references in the data analysis plan of your proposal. So an analysis plan should be developed in advance to guide data analysis. You don't begin to write data analysis plan after you have collected the data. This is the reason why you should consult a senior or supervisor, or better still, a statistician, to look at your statistical analysis plan at the stage of writing your proposal. So you don't think about analysis after the data has been collected, but rather you think about it right from the conception of your study, beginning from the time you are thinking about the research question, think about the variable to be collected, and think about what analysis will be done. So what does statistical significance mean? I think the rest of this lecture is just an attempt to answer some commonly asked questions. One, what does statistical analysis mean? Statistical significance is the likelihood that a relationship between two or more variables is caused by something other than chance. So in statistical hypothesis testing, we use this to determine whether to reject or not to reject non-hypothesis. What is statistical power in research? It is the probability of correctly rejecting null hypothesis that is false. It's also called statistical power. Okay, a related quantity to this statistical power is the type 2 error rate of the test, which is defined as probability of not rejecting a false null hypothesis. Because power assumes that null hypothesis is false, the computation of statistical power are conditional probability based on specific alternative values of the parameter being tested. As a probability, power will be ranging from 0 to 1, with larger value being more desirable, and numerically, power is defined as 1 minus beta. Beta, which is the type 2 error. I will try to explain this with using a simple illustration. And this illustration here simply shows the relationship among power, alpha, and beta. If you look at this 2 by 2 table, now the top row, I mean the horizontal line above show the in this case we are assuming null hypothesis, and if the null hypothesis is true, which is the reality, or if it is false in a reality, but your test says that you will reject null hypothesis if when it is true, then you have committed a type 1 error. But 1 minus type 1 error alpha gives you the confidence. In other words, we are saying that when your test says there's no relationship, that is, we reject, and it is all true and it is correct, then we are talking about the level of confidence. In other words, we are 95% sure, for instance, that the estimate you have obtained is correct and represent the true values. But when your test say reject null hypothesis, but this is not supposed to be rejected, then you have computed a type 2 error, and this is beta, and that is what is represented in this space here. But when there is a relationship, your test says there is a relationship, but there is no relationship, then that is type 1 error, which is shown here. So the opposite of type 1 error, or the difference between 1 and type 1 error, is actually called power. Okay, sorry, it's actually called the level of confidence, whereas the 1 minus beta error is called power. So please take your time, examine this relationship very well, then you will get a clearer picture of why we talk about power, why we talk about alpha and beta in sample size calculation. The scope of this lecture will not allow me to talk about sample size calculation, but I believe with this understanding, you'll be able to know why people choose the kind of sample size formula that they choose for their sample size. On this slide, I'm explaining further the relation between power, sample size, effect size, and alpha. Power is increased when a researcher increases the sample size, as well as when a researcher increases the effect size and significance level. A researcher wants both type 1 and type 2 error to be minimized, to be very minimal. The lower the alpha, the lower the power, and the higher the alpha, the higher the power. The lower the alpha, the less likely it is that you will make a type 1 error, and the lower the alpha, the more rigorous the test is. All of these are important because we need them to calculate sample size, and also to be able to infer that our statistics truly represent what it is in the population. An alpha of 0.01, for instance, means that the researcher is being relatively careful. She is only willing to risk being wrong 1 in 100 times in rejecting the null hypothesis when it is true. An alpha of 0.01 also mean that you have a 99% chance of saying there is no difference when there is in fact no difference. Increasing alpha increases the chance of making a type 1 error. Um, Saying there is a difference when there is not. Decreasing it, it decreases the chance of making a type 2 error, saying there is no difference when there is, and decrease the rigor of the test. When you increase alpha, you increases the power, because one will be rejecting the null hypothesis more often than accepting the alternative. And consequently, when the alpha is true, there is a greater chance of accepting it. And that gives the study good power. So I have put a list of references here that will be good for your further reading. Thank you very much for listening to me.